Okay, here was the, let's see, question number 1. So chapter 3 is an introduction to our reaction mechanisms, and to get us all on the same page when it comes to terminology. So for this reaction coordinate diagram, what was A? Reactants. B? Transition state or activated complex. I just used transition state. C? Intermediate. B, another transition state. And then D, the products. And then F is the activation energy, and E is the delta H of the reaction. Okay? And I didn't ask this question, but is this reaction exothermic or is it endothermic? I heard some immediate exos. Do we all agree with that? Well, we haven't decided if it's exo yet. Probably is if everybody says it is. Well, you never know. So, anybody want to go for endo? Okay. The reason it's exo is that the reactants have more energy than the products. So energy is going up in that. So in order for the reactants to get to products, they have to release energy, and that's our exothermic reaction. If the reactants started out at a lower energy than the products, they would have to gain energy, and that would be endo. So it's just a question of whether the reactants are higher or lower in energy than the products. Okay, so that was question number 1. Did anybody have any? Now what we have to do is we have to fill in specific structures for different reactions in this diagram, which we're going to do today. All right, so any questions about that one? Then number 2, there's 2 ways that we can either cleave or form a bond. And this is the first one. So which arrows would we have used in this reaction? Would we have used to cleave the carbon-chlorine bond? So would we have used A, B, C, D, E, or F? Well, let's see. I think, there's our scores. So most people said B. Then we've got a variety of answers of C, D, and E. Is B correct? Doesn't say, does it? Oh, it does up there. It says 69% of people got that correct. So B is the correct answer. So again, why? Well, so in this reaction, we end up with a carbocation and a chloride. So that means that both of the electrons had to go to the chlorine. That's going to leave the carbon with a positive charge and the chlorine with a negative charge. And so the arrow that we use for that is a full-headed arrow, indicating 2 electrons are moving. A half arrow means that 1 electron is moving. So we're moving the pair of electrons from the carbon to the chlorine, which is going to be B. And why do the electrons move from the carbon to the chlorine? Anyone?
Chlorine is much more electronegative.
So chlorine's more electronegative, and so it's going to get the electrons. The electrons will always move in the direction of more electronegativity. Okay. Right. Are we okay with that? And then number 3, I'm now going to form a bond from two species that have unpaired electrons. And so what kind of arrow do I show to form the carbon-chlorine bond from that? And so we have those choices, and A was the most popular answer at 27. 27 what? Oh, sorry, 17. So 27, that would put, there aren't that many people here. Okay, so A, so what's happening is the carbon's donating its unpaired electron, the chlorine's donating its unpaired electron, and we're forming the carbon-chlorine bond, so A with half arrows. Okay. So my goal here is to see where you're at. Does that make sense to everybody? Any questions on that? Okay. Any questions overall on the stuff in chapter 3? So here's what here's what we're going to do. So let's go through and look at the reactions here. Let's look at a couple of reactions that we're going to study in a couple of weeks. And we'll go through step by step the mechanism, reinforce these ideas of transition states, intermediates, and also the arrows. And there's going to be two types of reactions that we're going to do. And let me just give you, I don't know, we'll put this in a story. So, if you take ethyl chloride and you react it with hydroxide, you're going to get ethanol and chloride ion. What kind of reaction is that? Substitution? Do we all agree with that? That's a substitution reaction? Okay. It is. I'm substituting an OH for a Cl minus. Now, we have a term for molecules that have excess electrons or are electron rich. Species that are electron rich, meaning that they have either a lone pair or they have a lone pair with a negative charge. Those species we, in general chemistry, would have called like Lewis bases, right? They were donating electrons to the like H plus, that's a Lewis acid that could accept it. But in organic, we have a totally different set of terms. We call this a nucleophile. Literally translated to positive loving. So these are species that are electron rich, that are going to give their electrons or share their electrons with the electron poor. Okay. And in chemistry, everything is totally philanthropic, meaning that the electron richest always give to the electron poorest, and the electron rich don't give to each other. Okay, you can take that and relate it to the real world if you'd like, but in chemistry, it's always the rich give to the poor and the richest give to the poorest. Okay, if you have a choice. So those are nucleophiles. So these two, the hydroxide and the chloride, and if I wrote out the Lewis dot structures for each, they would have, chloride would have 4 pairs of electrons around it, oxygen would have 3. These are nucleophiles. And so the name of this reaction is nucleophilic substitution. because I'm substituting one nucleophile for another. Okay, so that's nucleophilic substitution, and it's abbreviated SN for substitution nucleophilic. Okay. All right. So when you do this reaction, there's some things that we want to know about the mechanisms. And so the first thing we do is we measure the rate equation. We determine the rate equation of this reaction. So when people do that, what happens is they double the concentration of the halide and keep the hydroxide the same. And then they would double the concentration of the hydroxide and keep the halide the same. Sort of like what you did in general chemistry when you had a chart of concentrations and then the rates. And what they found was that when you doubled the concentration of the chloride, that caused the rate to double as well. And when they doubled the concentration of the hydroxide, the rate doubled as well. I thought it was the keyboard doing that. Apparently not. Okay. So in general chemistry, what would we have done? We'd write a rate equation. We'd say, okay, well, the rate is equal to some rate constant times the concentration of the alkyl halide times the concentration of hydroxide, and then we would determine the rate order, and we would say, well, if I double the concentration of the alkyl halide and the rate doubles, what should the exponent be on the alkyl halide? It should be 1. Right. And if I double the concentration of the hydroxide and the rate doubles, that should also be 1. And if that doesn't quite make sense, if I doubled the concentration and the rate went up by 4, then that means the rate is equal to concentration squared. Because if I double the concentration, 2 squared would be 4. If I just have 1s there, then it doubles. Okay. So you can only get this information from the experiment. So people did these experiments and they found out that the reaction was first order in alkyl halide, and it was first order in hydroxide, and that then overall the reaction was what? Do you remember from General Chem? Overall it's second order. So that has to come from experiment. So people do the experiment, they find out it's first order in halide, it's first order in nucleophile, and overall it's second order. Okay. So then, okay, I'd like to know the mechanism. I'd like to know step by step how this reaction occurs. So the first easiest mechanism to write is to say, okay, the hydroxide comes in and attacks that carbon. And by attack, I mean it's donating its pair of electrons to the carbon to form a carbon-oxygen bond. So I'm using a full-headed arrow here, showing that it's going from the O minus to the carbon. Now, that carbon being attached to a chloride has a delta positive charge on it, because that's what it would be in the polar covalent bond. So my electrons and my arrows always go from negative to positive, or in this case to partial positive. Now if I stop there, what happens? Carbon has 5 bonds, that's still not allowed. So it kicks off chlorine. Or the carbon-chlorine bond breaks. And then the chloride becomes what we call a leaving group, because it's leaving. So I end up with my hydroxide attached to my carbon, and then my chloride is now free. That would be the simplest mechanism to think of. And so this would be called, when I teach general chemistry, this is what I call an elementary step of the mechanism. So being an elementary step of the mechanism, I'm allowed to write its rate equation from the stoichiometry of the reaction. Now I can't do that with the overall reaction. Up here we have, this is the overall reaction. You can never write the rate equation from the overall equation. It always has to be determined experimentally. But when I have the elementary step, I can write its rate equation. And so what I say here is, well, that rate would be some rate constant times the concentration of hydroxide times concentration of my alkyl halide and since there's one molecule of each, I would raise that to the first power. I can only do this for elementary steps of my mechanism. Everybody with me so far? So what am I looking for? When I'm writing my elementary steps, what am I trying to accomplish with that? Does anybody remember? How do I know if this is a possible elementary step? Its rate equation has to do what? Which Ken must have been a long time ago. A long time ago. Its rate equation has to match up with the overall rate equation. So if this is a one-step mechanism, this rate equation must match up to the overall rate equation. If it doesn't, then that's not a feasible step. If there's more than one step, then we have to talk about, well, which is the slow step, which we would call the rate determining step. See, it's all there. It just has to come back. So in this case, the simplest mechanism matches up with its rate equation to the overall rate equation. And the more complicated the mechanism, the more likely it is it's wrong. Because usually these things are going to try and be efficient. So this is indeed the mechanism. The hydroxide comes in, donates its pair of electrons to carbon, and kicks off the chlorine. Okay. And we know that because the rate equation is the same. And then we have to do some other things like we might want to try this with different molecules. We might want to rationalize why this happens. We might want to try different nucleophiles to see, because maybe nucleophiles, some are better than others, which means some should react faster than others, then maybe we should look at the leaving group, because some leaving groups will more easily leave than others. So we can go into all that detail, which we will later. Today it's just the introduction to the mechanism. So it looks like this one-step mechanism is okay. Now, it's one step, but it's called a bimolecular mechanism. We would call this bimolecular. The bimolecular term could come from the fact that in this reaction, in this elementary step, two molecules are reacting. It could also come from the fact that we have a sum of 2 from the exponents, because these exponents came from the stoichiometry. Okay, so actually this reaction is called an SN2 mechanism. It's nucleophilic substitution that is bimolecular in its kinetics and also in its mechanism. Okay. All right. Everybody with me? So somebody does this reaction, they measure the rate, they say, well, I'd like to know what the mechanism is, let me propose something. How about I propose the simplest mechanism, one step. Look, the rate equation equals the rate equation from before. I'm going to say that's the mechanism. And we have this bimolecular nucleophilic substitution. So, what kind of energy diagram would this have? If this is the one step in the mechanism, if I drew out its energy versus the reaction progress, I know I'm always going to have the reactants and the products. And I'm not going to worry about whether this is endo or exothermic right at the moment. But what goes in the middle? Looking at this mechanism, what should go in the middle? The energy's got to go up, right? And we've got to form a transition state. Are there any intermediates? No? Why not? Because there's only one step, and intermediates need 2 steps or more, because an intermediate, something that's formed in one step, reacts in the next step, so overall it cancels out. So you can't have an intermediate in a one-step mechanism. You can only have then one transition state going on to the final products. So there's its energy diagram. Goes through one transition state to the final products. Well, I want to know some more information about this. So I'll propose, what does a transition state look like? And there's a couple of transition states that we could come up with, and I'll refine those maybe later on once we know about what we call stereochemistry and chirality. But accept that this is the transition state for the moment. It is, but we'll prove it explicitly later. Here's what happens. The hydroxide comes in and it attacks the carbon down the carbon-chlorine bond. So the hydroxide comes in on that trajectory and it donates its pair of electrons to the carbon. So what would the transition state look like? First of all, what is the transition state? Transition state is a high energy species It's the top of the energy diagram. I cannot put a transition state in a bottle and study it because it's so high energy, it only exists for a small amount of time. And so I can't really study it. I can study it on the computer, but I can't really study it in the bottle. Now, I'm going to contrast that in a few minutes to intermediates, and I can put intermediates in the bottle. Sometimes they don't last very long. Other times they'll last like years. So an intermediate can be captured and studied. Transition state cannot. So the transition state is where I'm going to form and break bonds. Because that's all reactions are about, is breaking bonds and making bonds. And as you saw in the questions I asked at the beginning of class, there's two ways to do that, by moving a full pair of electrons or by moving one electron each. Sadly, we're going to get to the one electron each next semester in this book, because normally that would be the next thing we would talk about. So the transition state for this reaction looks like this. The hydroxide is coming into the carbon. And what happens is all the groups that are like this with the carbon, they're flattening out. So that when the highest energy species is going to have a partial bond to the carbon, a partial bond to the chlorine, and then the carbon is going to adopt a trigonal bipyramidal geometry. Now, for those of you saying you violated your 5 bonds to carbon rule, I did no such thing. Because there's a partial bond of the hydroxide and a partial bond of the chloride, I still only have 4 bonds. And this is a super high energy species, so those rules might not apply anyway. But this is what the structure looks like. And if you can kind of picture this, these groups are moving to become flattened out. So we use the dotted lines to indicate a partial bond, just like we did with resonance hybrids. And in terms of charges, the oxygen's going to go from -1 to on the other side having no formal charge. So all I know is it has some charge. And the chloride's going from having no formal charge to having a -1 formal charge on the other side. So you can also, what's happening is the oxygen is transferring some electron density to the carbon, or to the chlorine, as it leaves. So in the transition state then, we have partial bonds from the OH to the Cl, and we have partial negative bonds on the oxygen and the chloride. And so this is our transition state. And so this is the high energy species that's here in the diagram. So whenever we write a transition state, what we're doing is we're showing what bonds are being broken, what bonds are being made, and if there's any charges, we're averaging out the charges between the reactant and the product of that step. So oxygen going from -1 to 0, delta minus, chlorine going from 0 to -1, delta minus as well. So this is what that reaction looks like. And there's more evidence. Do I know that this hydroxide attacks from what we will call later on the backside? Yes, I know that is the case because of stereochemistry. And so I also know because if I change the nucleophile strength, the reaction rate will change. If I change the leaving group strength, the leaving group or the reaction rate will change. So I know all of this. So this mechanism has been worked out, but this is what it looks like. It's one step, hydroxide attacking carbon, going through this transition state to the final products. And it's a bimolecular mechanism. So I'm giving you examples of all these different terms that we're talking about. If I want the reaction to go faster, I need to somehow lower the transition state energy. And we'll get to that. Right? So that's SN1. And some organic reactions have people's names attached to them. This one doesn't. So I'm not totally clear what the history of all of this is. So then someone else, I'm sure, maybe the same person, said, all right, I'm going to change the structure of the halide. And now instead of using, what kind of carbon is this? Primary, secondary, or tertiary? What kind of carbon is that? Primary, secondary, or tertiary? Bless you. Primary. We agree? I don't see very many people agreeing, but I do. And that's all that matters. Why? Because it's got one carbon attached to it. Primary carbon. All right. So they decide to use what type of halide is this? The carbon attached to the chlorine is what kind of carbon? Tertiary. So they decide to use a tertiary carbon. And they get the same products. The hydroxide substitutes for the chloride. But then they go and they measure the rate equation. And all of a sudden, when they double the concentration of the alkyl halide, the rate doubles. But when they double the concentration of the hydroxide, the rate doesn't change. It stays the same. So, I mean, that had to be a pretty big find for somebody. I mean, I'm sure they had to do it numerous times because they didn't believe that. Probably had somebody else do it too. But the rate didn't change. Now, in general, when rate or rate equations change, the mechanism changes. So nowadays, if we did this reaction, we would immediately say, oh, this isn't the same mechanism. But it's still nucleophilic substitution. So now we have to decide, okay, what's the rate equation for this reaction? And the rate equation is equal to the concentration of, I'm going to just abbreviate the chloride like that, RCl, to the first power, and the hydroxide to the zero power. Because anything to the zero power is 1. And so basically that means that disappears. So the rate equation is only dependent on the alkyl halide. So now you got to come up with a mechanism whose rate equation looks like that. Well, guess what it isn't? It isn't the simplest one, right? Where the halide comes in, kicks off the leaving group in one step. Because we already know that's a bimolecular reaction. So people become a little bit creative and they say, okay, how about in the first step of the mechanism, the chlorine leaves. Forming a chloride and leaving the carbon with a positive charge. So that'll be my first step. That's elementary step 1. Then I say, okay, now that I have that carbon with the plus charge, my hydroxide then, being a nucleophile and having a pair of electrons that it can share, will come in and it will donate that pair of electrons. It is actually not donating, it's sharing, to form the final product. And so maybe it takes 2 steps for this mechanism instead of 1. And we know that's the case because 1 step doesn't have the same rate equation. Okay. So now we have 2-step mechanism. Now we have to ask ourselves a question: do these reactions occur at this? Do these rate steps occur at the same rate? Is one faster? Is one slower? And we need to know that because we need to determine, okay, which one of these is the rate determining step. And so we find out that, sure enough, the first step is the rate determining step. And the second step is really fast. So look at what we have here in these 2 steps. We have the full arrow giving the electrons to the chlorine, just like the first question I asked you, or second question, whatever question it was. And then in the second step, we have the full arrow of the pair of electrons going from the oxygen, sharing with the carbon to form the CO bond. The charges always have to add up on both sides. So no charge and a +1 -1, they cancel. On the other side, +1 -1 to a neutral. And now what's this carbon with the plus charge? What's that species called? It's the of the reaction of the mechanism. Hint, it's produced in the first step, used up in the second step, so that it doesn't show up overall in the overall equation. It is the intermediate. So this is now the intermediate of the reaction. So the rate determining step then would have a rate equation of this. It would be rate equals K times the concentration of the alkyl halide to the first, because that's the reactant in the first elementary step. Well, voila, there it is. I've now matched the rate in the elementary step to the rate, the overall rate equation. And actually, what I would then do in the second step is I would say, well, the rate is going to be, the rate equation for the second step is going to be the same as the SN2 rate equation of alkyl halide times hydroxide, but I won't get into that. So which rate step matches the overall rate? That's the rate determining step. So that's another way we can determine the rate determining step. I'm just kind of saying that's what it is. And it matches up. So here's the mechanism of this reaction. It changed. It is now a unimolecular reaction, so this is now called SN1. And so now I have a reaction that has reactants, products, a transition state into an intermediate, into another transition state, into the products. So that's what its reaction coordinate diagram would look like. I know what the intermediate is. The intermediate is the C+. And then I have the two transition states. So if this is the mechanism. This is a two-step mechanism. So in the book they have the one-step mechanism, the two-step mechanisms. These are the ones they're using because these are the ones that are going to be most important. SN1 and SN2. But I don't know that I buy that. Well, then you have to go through and you have to say, well, do I have any evidence that that intermediate exists? And people spent a lot of time in the 60s looking at carbocations. A lot of time. Trying to show that they existed. And then what their structural parameters were. And the real simple structural parameter is a tertiary carbocation is more stable than a secondary carbocation, which is infinitely more stable than a primary carbocation, because a primary carbocation does not exist this semester. And people came up with that. And you might say, well, why? How do you get that? Well, a carbocation has, 6 electrons? It's not happy. It's not stable. So every time I put a carbon on that carbocation, remember the carbon is slightly more electronegative than each of the hydrogens. So every carbon of an alkyl group has a slightly negative charge, meaning it has some electron density. And what it can do is it can push some of that electron density into the carbocation. So the carbocation isn't necessarily sitting at 6 electrons, it might be sitting at 6.2 for every methyl group that's attached. Well, if you want to make that carbocation the most stable, attach the most methyl groups to it. And one methyl group isn't enough. Okay? So tertiary carbocations are more stable than secondaries. And how does that affect the rate? We'll have to do that on Friday. Kind of pick this up and take it into the final part of chapter 3. So that's where we're at. This is like probably 4 lectures compressed into one. And when we get to these guys in a couple weeks, I'm going to say, remember we did this? And then you're going to be, no, I don't remember that. And we'll figure it out from there. Okay? So I think the next reading is basically finishing up chapter 3. That means that the problems in reading in chapter 3 won't be due until Friday at midnight. When the deadline passes on a homework or on reading, the problems disappear. And then I have to make them come back. So that's why they disappeared over the weekend. And then I made them come back for chapter 2. Okay. All right, if you have any questions, come and see me. Otherwise, we'll pick up from here and go into the rest of chapter 3.
Hi, I just wanted to remind you that I'm coming to lab